In this video, we're going to talk about multi-step profiles and catalysts. So in the previous lesson, we talked about reaction profiles. So a reaction profile, also known as a potential energy diagram, shows your reactants, your activation energy, and then your products. Now, if you have a two-step reaction, you're going to have two transition states that are going to be shown on your profile. So in the one that I just sketched down here, this is a single step. My transition state is up at the top of my hill. And remember, a transition state is where you may have two molecules, they slam together, they're stuck together temporarily before the bonds break and you have new molecules. Likewise, if you had a three-step reaction, you'd have three transition state shown. So you'd have multiple hills going on your profile. The rate determining step is going to have the highest activation energy. It's got the largest hill that you need to overcome. So on our profile here, that is your activation energy. Again, this is only a single step reaction profile. Now, in a multi-step profile, intermediates are going to be valleys that you'll see between the reactants and the products. So let's take a look at a multi-step profile. So here we have two steps. We have two different activation energies. And if you notice, our first hill here is much larger than the second hill. So our first step is going to be our slow step. It's going to be our rate determining step because it takes the most amount of energy to overcome that hill. It is going to be exothermic. Exothermic means you are releasing energy. So you start with energy here and you end with energy here. So you start at 1, you end at 2. 2 is much lower energy than 1, so that energy must have been released. It's an exothermic. Now, an endothermic reaction would be the opposite. So in an endothermic reaction, you're going to end up with more energy than you started with. So if I start here and end with a higher energy, that would be an endothermic reaction. And just like I mentioned on the previous slide, our valleys are where the intermediates are going to exist. Okay, so intermediates exist at those valleys in a multi-step profile. All right, so let's dig in with an example here. So it says construct a reaction profile using the following information below regarding the transformation of T-butyl bromine into T-butanol in the presence of hydroxide. So we have two steps here. We have two delta H values. And we have, we know that the first step is going to be our slow step, so that hill is going to be much larger than the second hill. And that's it. Let's dig in. So when we draw our reaction profiles for a multi-step reaction, on our y-axis is going to be our energy. Energy will increase as I move up on my profile. And going to the right is going to be our reaction progress. So as I move to the right, my reaction will progress. Okay, so let's start with our reactants. Okay, and it's telling us that first step is going to be our slow step. So it's going to have a much higher peak than our second step here. Okay. Now, our delta H between the first step and where we end up, our intermediate, is going to be a change of 90 kilojoules. So it's going to be endothermic. So that means our plateau, our intermediate for that first step, is going to be higher than where we started. Okay, so this is our intermediate. Okay, so because this number is positive, it's endothermic. So again, I'm going to end up higher than where I started because it's endothermic. It's positive. Okay. The next step is our fast step. So my activation energy should not be as high as the first step. So the activation energy here, we can label this EA1, should be greater than our second step. Our second step is also negative, meaning it's exothermic. So I should end with less energy than I started with. So I'm releasing energy. So let's see, let's do a smaller hill here, and then let's end up down here perhaps. So I'm going to label the second one EA2. That's the second activation energy that I needed here. And then all the way on the right side would be our products on the other side. So again, we started with our reactants. We had our first activation energy. We ended up as an intermediate. We had our second reaction, and then we ended up as a product. And again, first delta H is positive, so that means it is endothermic. So we're going to end higher than we started with. Our second delta H, our enthalpy, is negative, so we're going to end lower than we started in that second reaction. And that's a multi-step profile. Now let's do something a little more exact. Let's graph this. Okay, so that last one we just kind of sketched it. Let's make a reaction profile that is exact here. So I have a grid, and we've got some information in the table here on the left. So it tells us that our reactants are 20 kilojoules. So I'm going to start by drawing a line at 20. And let's use a different color so it pops a little more. Okay, so that's going to be our reactants. It tells us transition state 1 exists at 80 kilojoules. So I'm going to draw a dot here at 80. And I'm going to connect my dots here. Connect my line to my dot. It tells us our intermediate occurs at 50 kilojoules. So 50 is down here. So let's draw a dot down here at 50. Connect the dots. This is kind of like a game. Transition state 2 is at 90. So I'm going to go back up and here. And let's connect the dots. And then finally our products are at 5. So that would be 10. So 5 would be down here. And done. Okay. So our intermediate, again, is this valley right here. This is a two-step reaction. We have two steps going on here. So our first step, we went from 20 to 80. That's our first activation energy. Our second one, we went from 50 up to 90. So this should be EA1, EA2. We have two transition states. This would be transition state 1. This would be transition state 2. Okay, so we have a multi-step profile here. Again, overall, this would be an exothermic reaction. So I started at 20 and I ended at 5, so I lost energy. So overall, it is an exothermic reaction. My first step was an endothermic reaction because I ended with more energy than I started with. My second step was exothermic because I started with this intermediate and I ended with less energy than I started with. So exothermic in that second step. So this is just another example of a multi-step profile. So you can have several steps involved. Each step is going to be a peak on our graph. All right, let's talk about catalysts. So you may have heard the word catalyst before. Catalyst is used all the time. So let's say you have, I don't know, an angry mob. And maybe the catalyst for that mob is somebody that throws something at the police. And now the police rush in and take out the angry mob. That's used all the time in the news. So a catalyst is something that speeds up a chemical reaction. Or in the example of our angry mob, a catalyst is something that caused the reaction to happen. It caused the police to rush in much faster. Okay, so you'll hear the word catalyst used often in the news, and it means something similar in terms of chemistry. So it's something that's used to speed up a chemical reaction. Now, in a chemical reaction, it is not consumed by the reaction like an intermediate is. Okay, so intermediates are produced and then used up. Catalyst is not the same. So we'll look at some examples where a catalyst is involved. But an important thing to understand is a catalyst is regenerated by the end of the reaction and can be used to catalyze more reactions. So a catalyst will speed up the reaction and it will regenerate itself in the reaction to cause the reaction to happen again. And when we look at an example here, you'll see what I mean when we're looking at a catalyst. Okay, if you recall, a catalyst lowers the activation energy. So if I have a reaction profile, I have a certain activation energy. A catalyst lowers the requirements, so it's going to lower the activation energy of a reaction. That's the purpose of a catalyst. So again, it lowers the bar and makes the reaction happen with less activation energy. We have two types of catalysts. You have a homogeneous catalyst, homo meaning the same. So it is going to be uniform when it mixes because it's in the same phase as the reactants. Next, you have a heterogeneous catalyst, or different, so it's going to be in a different phase from the reactants. So you could have a solid catalyst with gaseous reactants versus just maybe gases and liquids mixing together in the case of a homogeneous catalyst. All right, let's look at an example here. In this example, it says the rate of decomposition of hydrogen peroxide can be increased by adding a homogeneous catalyst. So again, homo meaning the same, it's going to be the same phase. The reaction mechanism occurs in two steps as shown below. Write the overall reaction, identify the catalyst, and identify the intermediates. So let's look at a few things here. So if you're looking at both reactions, a couple things might pop out because they appear multiple times. So let's start with intermediates. Okay, since we've talked about intermediates before, let's see where an intermediate is. So remember, an intermediate is produced and then used up. Okay, so an intermediate is produced and then used up, or then consumed. So if you're looking at our two reactions, you'll notice that our IO minus is produced in the first reaction, and then it is used as a reactant in the second reaction. So that would be an intermediate because it is produced and then it is used up in the reaction. Now, a catalyst, let's use a different color here. A catalyst is consumed and then produced. So kind of the opposite. Okay, so a catalyst is consumed and then produced. So if you're looking at the reaction, you should notice that we have an iodine ion that is used in the reaction, and then it is produced as one of our final products. So that would be an example of a catalyst. If I were to write the overall reaction, I would cancel out anything that exists on both sides. So our catalyst and our intermediates are going to be eliminated from our equation. So if I were to write the entire reaction, so after crossing off our catalysts and intermediates, if I added what's on the left-hand side of our reaction with what's on the right side of our reaction, I have two of these H2O2s, our peroxides. Those are aqueous. And those are going to decompose into two waters in the liquid state. And then we'll have an O2 left over. So catalysts are not really part of the reaction, just like intermediates. They're there to serve a purpose, but they're not part of the actual reaction. So we eliminate those when we're writing our final reaction. And that's it. So we talked about multi-step profiles, and we also talked about catalyst in this lesson.